Today, we have the pleasure of having Daniel Hoff, Lowell. And Dan, as you see in his brief bio there, received his PhD from the Washington University at St. Louis, working with Sobotka. And he has many interests in nuclear physics. And today, in particular, he will tell us about his recent work on the nuclear mirror-symmetry. And just a brief announcement. The next presentation in 2 weeks from today will be by Ji Chen from Hf NSCL, and she will telling us about proving exotic structure with one nuclear transfer. So with that, I will pass the screen to Dan. And if you have any questions during the talk, please put it in the chat or raise your hand. We can always, of course, defer all the questions for the end, but depending on the questions and the urgency of that, we can ask as we go. Okay, Dan, welcome. All yours.
Great. Yeah, thank you for the introduction, Augusto. And I'd like to thank all the organizers of this seminar series for inviting me to share this work with you. So yeah, today I'm going to talk about a crack in nuclear mirror symmetry. And really this, I'll be focusing on this recent work that we published back in April, showing evidence for mirror symmetry violation in bound nuclear ground states. And to give you a little outline of the talk, I will briefly talk about symmetries in physics, and then I'll spend most of the talk talking about isospin or isobaric spin symmetry and how that manifests in nuclei. I'll then go over the experiment that was done at the NSCL looking at strontium-73. And then I'll go over the evidence for mirror symmetry breaking in the mirror pair strontium-73 and bromine-73. And then I'll give a little summary for you guys. So this idea of symmetries in physics, you know, I think a lot of us, when we think of this, we think of Emmy Noether and her theorem that she came up with in the early 1900s. And if I had to paraphrase this, you know, basically what it says is that for every symmetry present in a physical system, there's a corresponding conservation law. And I'd say a sort of corollary to that is that when a symmetry breaks down, it often tells us that our understanding is incomplete. And you know, there's lots of examples of this. You know, I think a big question that you know people are still talking about is you know, the matter-antimatter asymmetry. You know, why is our universe dominated by matter? And this is a very big question in physics. And I think another great example is the parity violation in weak decays, of course, observed in C.S. Wu's famous experiment. And so when it comes to isospin symmetry and nuclei, this was first sort of posited by Heisenberg in the early 1930s. He noticed that there were a lot of, you know, this was shortly after the discovery of the neutron, and he noticed that there were a lot of similarities between protons and neutrons. And so he posited that perhaps you could think of these as manifestations of a single object, you know, a nucleon with isospin symmetry, and then the proton and neutron would be different projections of this symmetry. And this was really extended to nuclei by Wigner in a few years later. And you know, in a much similar way, as you can talk about the spin of nuclei as being the combination of all the protons and neutrons in their orbits to get a final spin, a total spin. You can do a similar thing with isospin and assign total isospin to different nuclei. So in example here in the A equals 9 isobar, this plus 3/2 projection for this 3/2 isospin would be the ground state of lithium-9. Minus 3/2 projection would be the ground state in carbon-9. And then there should be isobaric-analog states, excited states in beryllium-9 and boron-9 that correspond to these projections. So the projection of isospin tells you about the asymmetry between the protons and neutrons, and really defines the nucleus that you're talking about. And a big consequence of this is when you look at nuclei with exchanged proton and neutron numbers, these are called mirror nuclei, and they should have a very similar set of states. But of course, this symmetry is broken. Since pretty much it's known to be broken since it was even first positive, as protons and neutrons do have slightly different masses. They have slightly different spins, or magnetic moments rather. And even still, the interaction, we know now that the interactions between neutron-neutron, proton-proton, and even neutron-proton pairs are slightly different. And then of course, on top of that, protons have charge. And so the Coulomb interaction is really the major source of isospin symmetry breaking in nuclei. And even, early on, it was thought that isospin symmetry might not be of much use in heavier nuclei, but it has remained a really surprisingly robust symmetry. And that's really reflected when you look at the level structures between nuclei. But just to give you a sense of how this is broken by the Coulomb force, just wanted to go over Coulomb energy in nuclei. So in our sort of standard shell model picture, if the protons had no charge, we fill up these different potential wells for the neutrons and protons. And if there was no charge in the protons, then the states would be virtually identical because the interactions are very similar. And so you would expect, mirror nuclei to be very similar in mass. Of course, protons do have charge, so this situation is more similar to this picture on the right, where once you turn on the Coulomb force, this shifts the energy levels for the protons. And so this will, this means that they'll have different masses, these mirror nuclei. And just to give you a sense of scales here, so for the case of bromine 73, say, the mass itself is about 70 GeV. The Coulomb forces just from the protons is about 20 MeV. And so it was found, using some perturbation theory and the Wigner-Eckert theorem, you can derive what's now been established as the isobaric mass multiplet equation, which basically says that these masses along these isobars will follow this sort of quadratic formula. And this is kind of diagrammed here in this picture on the left, where say if you have some neutron-rich nucleus and then you interchange the proton and neutron number, you expect there to be some Coulomb shift. And again, this should go about quadratically along an isobar. And just to show you a couple examples of this, here you can see a IMME plot, in this case for the A equals 16 isobar. And I'll point out that fluorine 16 here is missing. Might touch on that a little bit later. And here what's shown is basically the difference in mass excess with respect to this fitted IMME equation. And the thing I wanted to point out here is that these effects or deviations would be on the order of about keV here. And you can keep extending this to heavier and heavier systems. So here's an example in the A equals 20 isobar. Again, these differences with the IMME residual is on the order of a few keV. And even recently there was a paper claiming that as you go higher and higher in mass number, you may even need to include a cubic term. And so this could tell you then about, how is this picture of the IMME breaking down if you needed this cubic term. But you know, this picture also works for excited states in nuclei, and I think this is shown well by some of these figures here. These comparing excited states in different mirror nuclei. So this case on the left shows an example from 48 manganese and 48 vanadium, and these experiments, you know, these were populated in fusion evaporation experiments. You populate some high spin states and you watch the gamma ray cascades come down. And when you look at the energies of these different excited levels and even, you know, the strength of the gamma ray transitions, there's, you know, surprisingly similar. And this really shows the sort of robustness of the symmetry even in these heavier nuclei. And on the right here, you can see an example from 51 iron and 51 manganese. And in fact, in this this work, they were talking about what can you learn from actually the shifts in energy differences between these levels, or mirror energy differences. And on that, I kind of wanted to highlight some recent works kind of probing what these mirror energy differences and consequences on isospin symmetry breaking are. So on the left here, we have a fairly recent PRL comparing 52 nickel and 52 chromium, and then 51 cobalt and 51 chromium. And these, and really what these were looking at is then trying to describe these mirror energy differences, the shifts between the excitation energies with a shell model. And in fact, what they found is that in order to really describe these changes as you go to higher spin, you actually needed to include a spin-dependent isospin symmetry breaking term. And in fact, in this other case, even more recent, looking at 52 cobalt, 52 manganese, they said that in fact, you needed to include multiple spin-dependent isospin breaking terms to really have the shell model predictions line up with the experiment. Okay, so you know, the thing about isospin symmetry, though, is that, you know, because this is, you know, looking at these mirror nuclei, you have to exchange proton and neutron number. What that means is that you can only really test this near the n equals z line. And of course, you know, then there will be some sort of last mirror pair that you can look at as the heavier elements bend over, or the line of stability bends over to higher neutron number at heavier nuclei. So to sort of get a grander picture of this, you know, we thought you could maybe sort of replot the chart of nuclides, focusing on this n equals z line. And to do this, you know, we can just kind of start plotting from the ground up the different isobar multiplets, you know, starting from protons and neutrons, and then going to t equals 1 systems, like the deuteron, proton, proton, neutron, neutron. We can kind of keep building this up to give ourselves a picture of how does this mirror symmetry behave, at least with respect to ground states of nuclei. So what I show here is a plot of the known mirror nuclides that have the same ground state structure. And what you'll notice is that, you know, for almost the entire known chart of nuclides, the ground states of nuclei seem to obey this isospin symmetry. So their nuclear structure is the same. And this is kind of reflected too if you look along an isobar and you sort of account for the Coulomb energy shift, then you can start to make connection between states along the isobar. So down here for this A equals 9 system that I mentioned before, you can see the ground states carbon 9, lithium 9. There's some, the boron 9 and beryllium 9 ground states would be T equals 1/2 in this case, but then there would be excited states in those nuclei that are these isobaric analog states that should be, you know, roughly identical to these ground states of carbon 9, lithium 9. But on this chart, you'll notice a couple spots where these black squares or cracks in this mirror chart. And so down here, this is these two spots here correspond to the case of fluorine-16 and nitrogen-16. And in this case, actually fluorine-16 is particle unbound. And due to this weak binding, this actually gives rise to a Thomas-Ullmann shift effect that actually rearranges the low-lying states in fluorine-16 with respect to nitrogen-16. And so they end up having different ground state structures. And if anyone's interested, I have a couple slides about that that I could show later. The other region that you might notice is up here, this A equals 73 isobar. And what's interesting about this case is, in this case, these strontium-73 and bromine-73 are bound nuclei. So it's not clear that it can't really be this Thomas-Ullmann shift. So this tells us that perhaps something else a little more interesting is going on. And so with that, I'll move on to talking about the actual experiment we did showing this evidence for this mirror-symmetry violation. And actually, the original motivation for this experiment was to measure properties about rubidium-73 through the beta-delayed proton emission of strontium-73. And the reason for looking at the structure of rubidium-73 is because it has astrophysical implications in the rapid proton capture process that's thought to occur in thermonuclear X-ray bursts. And one site for this is kind of the picture that I'm showing down here, where you have a neutron star in a binary system with a more normal star. And as the hydrogen and helium-rich matter from the companion star accrete onto the neutron star, as that matter hits the surface of the neutron star, you can have this rapid proton capture process happen, creating these X-ray bursts. And so the idea here is, if you have some proton captures, you might have, you'll have some beta decays back once the nuclei are proton unbound. And in particular, if you reach 72 krypton and you try to, there's a proton capture onto 72 krypton, since rubidium-73 in this case is proton unbound, that means a proton capture would happen and it might just fall back apart. So understanding the proton separation energy of rubidium-73 would tell you, how likely is that process to happen, and whether you could bypass this waiting point. So really, our goal was to understand the structure of rubidium-73. And so to do this, we did this as a implant decay experiment. And to give you kind of a picture of what you might expect from this, so we're going to implant strontium-73 into an active detector and watch for the beta-delayed proton emission. And the detector was surrounded by high purity germanium array to look at gamma rays in coincidence with these decays. And on the right here, I just show maybe what you'd expect for a typical picture of this kind of process, or maybe even beta-delayed neutron process. And the idea here is you'd have some parent nucleus, and this could beta decay to some states above say the proton decay threshold, which then could proton decay, and maybe you get some gamma rays from the overall daughter nucleus. But then it could also beta decay to particle bound states, which would then gamma decay. But the situation for strontium-73 is a little bit different, because in this case, rubidium-73, as I mentioned, is completely proton unbound. So that means any beta decays of strontium-73 will be followed by a proton emitted from the populated state in rubidium-73. And so this experiment was, as I mentioned, done at the NSCL, where a 140 MeV per nucleon 92 molybdenum primary beam was used. And this was fragmented on a beryllium production target. And then the fragments were passed through the A1900 fragment separator with a strontium-73. Sent to us was a strontium-73 cocktail beam. And I really should mention that this experiment was really enabled by the radio frequency fragment separator. So this is a known problem on the proton-rich side of the chart. that you can have a low momentum tails of many of the fragments. And so by using this radio frequency fragment separator, we were able to purify the beam by a factor of 4,500. And the way this kind of works is, so here's a schematic of it. It's essentially a radio frequency cavity that, and the ions, as they're passed from the fragment separator, will be spaced out in time with different velocities. And so the idea here is that you tune the separator such that the ion that you're interested in will feel the full effects of the radio frequency field and be deflected above a blocker, which will then block the ions that you're not interested in. And again, like I said, this really enabled the experiment, reducing the rate and purifying the beam and cut down on the background significantly. And here you can see a picture from the experimental end station. Just a little bit of ways up the beam line. On the left here was the radio frequency fragment separator. The beam came in, passed through a pin detector, an aluminum degrader, and then was implanted in the middle of the segmented germanium array, or SEGA here. And in the middle of this, you can see the beta counting station stack, this picture on the right here. And the main thing I wanted to point out on this was actually the double-sided silicon strip detector that was used as the implantation detector. And using this highly segmented silicon detector allowed us to cut down on the background a lot, which I'll touch on in a second. And of course, here's Chris Morse. And for some of you that may have seen a version of this talk before, I actually wasn't a part of the experiment, and Chris was the postdoc preceding me, but I really would like to thank him for all his work and designing and setting up and executing this experiment and making sure that it was a success. So here is a picture on the right here of a sort of better or easier picture to look at for the experiment. And again, the beam is coming into the stack here, and it's being implanted into this double-sided silicon strip detector. And on the bottom left here, you can see kind of an idea of what's going on. So the ions of interest will be implanted into it, and we're able to localize a pixel where the implantation event happened, and then look for decays with a little bit of tolerance around them. And I think a decent way to sort of think about this is, because it's highly segmented, for each time that we're able to define an implant pixel and some tolerance, it's essentially like looking at it as a totally separate detector. And in that way, you're able to cut down on the background rate, even though it's being implanted into the same sort of detector. And of course, we're then able to do time correlations between the implants and the decays to look at the ions actually decaying, as well as get the relevant energy information as well. And so on the right here, I'm showing a particle identification plot from the experiment, where on the y-axis here we have the energy dropped in the first silicon pin detector, and then on the x-axis, the time of flight from the A1900 fragment separator to the experimental end station. And you see quite a few features on this plot here. There's actually, this is zoomed in, there's actually quite a few more, and you can even see the gap from the filtered ions from the radio frequency fragment separator. But, and you also kind of see there's a bit of streaks and some other things. But thankfully for the ions that we were interested in for this particular analysis, strontium-73, these are well separated from the rest of these ions. So we were able to just focus on these strontium-73 ions. So looking at these in more detail, you'll see these are the decay spectra from the experiment. And on the left here, I'm showing the implant decay correlation time, between the implant of strontium-73 and when a potential decay event was found. And you'll see that this curve here, the time correlation, is well described by a single species exponentially decaying with a flat random uncorrelated background. And if you go ahead and make a time gate on these events and look at the energies, you get the spectrum on the right here. And I'll point out also that this blue region at the bottom here, this corresponds to the measured background that was taken by looking at the energy of these uncorrelated background events much further in time from the decay of strontium-73. And you'll also notice for these peaks here that have been fit, they're kind of broadened out and they have these sort of long tails here. And this is actually because we do capture some of the beta energy in the detector, and these leave a Landau distribution of energies. However, the protons that are emitted are fully stopped in the detector, so these will provide a nice Gaussian peak. So this kind of broadening and shift in the energies is referred to as beta summing. And before I talk about what these features are, I think it's good to kind of look at this with a level scheme next to it. So again, we're implanting strontium-73. This is going to beta decay primarily to the isobaric analog state in rubidium-73, which will then proton decay. And so when looking at this strongest peak here, after doing a beta summing correction and also accounting for the fact that we actually capture the recoil nucleus or the recoil energy in the detector, the proton energy that we find for this peak here it agrees very well with the previous direct measurement that measured the proton energy from the decay from this isobaric analog state to the ground state of 72 krypton. So that tells us that this peak here is primarily proton decays to the ground state from the isobaric analog state. But you'll notice the second feature that's about 700 keV lower in energy. And actually, when we if you gate on this secondary peak and look at the gamma rays in coincidence with it, that's shown in the top right here, we see quite a few number of 709 keV gamma rays. And these are known to correspond to a de-excitation from the 2+ state in 72 krypton to the ground state. And so because the secondary peak is about 700 keV lower, and we see this good number of these 709 keV gamma rays, that tells us that the population of this secondary peak is largely proton decays from the isobaric analog state to the 2+ state in 72 krypton. And so our next sort of question then was, okay, so we have this decay spectrum from the isobaric analog state. What does that tell us about the structure of this isobaric analog state? And then by extension, because this is a super allowed decay, that would tell us about the structure of the ground state of strontium-73, which this is decaying from. And so, on top of that, when you look at previous experiments in a similar mass region that I'm showing here, the situation becomes a little more complicated. So if we look, for example, in the case of beta delayed proton emission from 65 selenium, in this case, 65 selenium supposedly has a 3/2 ground state. That means the isobaric analog state in 65 arsenic would also be 3/2. And when you look at the proton spectrum here, we see mostly just one strong peak and no real gamma rays in coincidence with that. And so that tells us that the protons from this state are primarily decaying to the ground state of 64 germanium. If you then go to the case of 69 krypton, this supposedly has a 5/2 ground state. And so the isobaric analog state in 69 bromine will should have 5/2 spin. And when you look at the proton spectra for this, there's really only one main peak. And in coincidence with this are a good number of gamma rays, a little over 850 keV, which corresponds to the de-excitation of the 2+ state in 68 selenium to the ground state. So then what this is suggesting is that perhaps due to angular momentum barriers, this isobaric analog state is primarily decaying to the 2+ state in 68 selenium. However, when you look at the spectrum that we observed, we see quite a significant branching to both of these states, right? And so to really understand this, we reached out to some of our theorist colleagues at Michigan State, in particular, Simon Wang, who at the time was a postdoc for Vitek Nazarevich. He did some Gamow coupled channel calculations for us. And so for these, essentially what these amounted to is that we treated rubidium-73 as a deformed 72 krypton core with a valence proton in that orbit. And the situation for the A equals 73 case is a little bit different than the cases I just showed, because we know that deformation is playing a strong role in the structure of these nuclei. So in order to understand this, Simon did the calculations with two different deformations, oblate deformation and a prolate deformation, and then the proton being in a couple different orbits, so 5½ minus and 1½ minus. And the main thing to pay attention to here are the branching ratios in this table. And if you look closely, what you see is that the only case that really, the only solution that really was similar to the experiment was the case when you treated 72 krypton as oblately deformed and the proton being in a 5½ minus orbit. And in this case, then the small p wave component here allowed for a significant branching to this 2+ state, more or less putting the branches on the same order here, much like we observed in the experiment. So, that's great. So now we can kind of say, well, it looks like the isobaric-analog state in rubidium-73 is 5½ minus. By extension, then the ground state of strontium-73 should also be 5½ minus. But when you look in the mirror nucleus to strontium-73, bromine-73, it purportedly has a 1½ minus ground state with an almost degenerate 5½ minus state. And so this suggests that there is some rearrangement of the levels going on, and I'll touch on perhaps some of the examples or why that might be the case in a second. But I should also mention that we were able to actually achieve the goal of the experiment, finding the proton separation energy of rubidium-73. So on the right here, I show updated decay spectrum from the experiment. You'll notice that the blue region here is greatly reduced. We were able to optimize the analysis to greatly reduce the background. And we do see some evidence for a low-lying peak that we think corresponds from proton decays from the ground state of rubidium-73 to the ground state of 72 krypton. And with this, we're able to fully constrain then the proton separation energy, really solidifying 72 krypton as being a waiting point in the RP process. And I'm happy to say just earlier this week, these results were accepted in PRC. And we also do a detailed analysis on the influence of this updated separation energy on how this affects the RP process. So I would watch out for that. So to actually get this ground state energy or this proton separation energy, we did a Bayesian analysis for this. I kind of caught the bug for the Bayesian analysis, and so I thought this would be a really good case to kind of do this for the first time for myself. And so to do this, I used the MC Python package, which is a Markov chain Monte Carlo method. And with this, you can see the resulting plots from the analysis here. So on the diagonal here, these are the posterior probabilities, or rather, the parameter estimations for the fit to the peaks in this region of interest. And then these off diagonals here show the correlations between the parameters. So in the case that we just considered 2 peaks in this region of interest down here, we can see that these the parameters are well constrained. But what's kind of nice about this kind of analysis is that you can ask, it's kind of easier to ask questions. So, of course, we wanted to know, what would be the results if there were 3 peaks down in this low region down here. So you can see the results of that on the right here, where now the correlations between parameters, this is really not constrained very well. And so, of course, then you also want to ask, well, which model does your data prefer? And so to do that, we investigated this by calculating the Bayes factor via thermodynamic annealing. So by comparing the Bayes factor, that should give you a kind of idea of which model does your data prefer. In fact, what we found was that our data did not prefer one of these models over the other. And actually, we interpret that to mean that our data is not sufficient to say whether there are more than or if there's another transition in this region of interest. However, the number that we report in the paper is using this doublet model, which does still well constrain the proton separation energy, which is actually also constrained by non-observations of it, putting constraints on the half-life. So actually, with the data that we do have, we think it's completely, that the proton separation energy is completely constrained. And actually, since we have information on the ground state energy of rubidium-73, that does mean that we can make IMME predictions for the ground state mass of strontium-73. So on the right here, you can see fits to the IMME here, and the differences here with this red band being the 1 sigma confidence limits for the mass of strontium-73. And in blue here with these bigger error bars, these are the predictions from the latest atomic mass evaluations. So our result does agree well. We get a very similar result for the ground state mass of strontium-73, but we were able to better constrain what the mass should be. And also with this, since we're able to get a measure of the ground state energy of rubidium-73, there were actually some very recent studies that were looking at mirror energy differences between ground states to see how much isospin breaking was needed in DFT calculations. And that's shown on the right here for a wide range of systems. And in particular, what I want to point out here is that these solid points here correspond to known masses that were included in the fits for these calculations, and the open squares correspond to nuclei that weren't known. And in fact, if you look here, so the T equals 1/2 case for A equals 73, now that we're able to get put a constraint on the ground state mass of rubidium-73, this can add another data point to these studies. And so in summary, what we've shown is that it appears that the ground state of strontium-73 is different with respect to its mirror bromine-73 in violation of this mirror symmetry. And now the question is really, how can that come about, right? So it's likely the rearrangement of this almost degenerate ground state between the mirror pair. And me being the big skeptic that I am, it could be the case that bromine-73 was assigned the wrong spin. There are a lot of convincing gamma ray measurements that deduce that it should be 1/2 minus, but there are no direct measurements. It could also be the case that there's some shape coexistence going on. So we know in this region of the chart that there is a significant amount of shape coexistence. And so perhaps the shape of the 1/2 minus and 5/2 minus states in this mirror pair are different deformations, and that could give rise to this rearrangement. And of course, it could also be the case that there's some charge symmetry breaking in the nucleon-nucleon force that needs to be included in the calculations to really, or not calculations, but to actually predict this inversion. So of course, these kind of measurements or discoveries are very exciting to someone like me as an experimentalist, because this tells us that we should go do some more experiments. So again, to get to the case of whether bromine 73 actually is 1/2 minus, you could think about doing beta NMR measurements of bromine 73. And actually that could be done with current technologies right now. And then of course, to fully confirm this mirror symmetry breaking, you could do a similar beta NMR measurement on strontium 73 to really say that this is actually what's going on. And of course, then understanding the IMME it can also probe isospin symmetry breaking effects. So I think it would be very nice to do a precision mass measurement of strontium 73 to test the IMME. And actually with some new technologies, I think that this actually could be possible. And of course, I have to mention a very recent paper that was just published a couple weeks ago. Actually, Augusto was a part of, looking for or trying to explain this isospin symmetry breaking in this mirror pair. And interestingly, they do find from their shell model calculations that, of course, the Coulomb energy differences are dominating this rearrangement. But in fact, you may need a small, few dozen keV isospin symmetry breaking term to really explain this rearrangement of states. So with that, I would like to thank all of my collaborators. I'd also like to specifically thank Tom Ginter, the beam physicist for this experiment, who really made it possible, delivering the strontium 73 beam for the experiment. I also provide a public access link to the paper if you'd like to look at it in more detail. And I'd like to thank you for your attention, and I'd be happy to answer any questions.
Well, I'm going to give you a very nice presentation, Dan. Thank you so much. Let me open the seminar for questions or comments from the audience. I'm looking if there is any hands that are being raised. By the way, everybody should know there will be a copy of Dan's talk on the website, and as well as the video of the talk. So we have one question here from Grisha.
Okay, so yeah, very, very exciting results. I have the following question. Is it possible to explain this relatively small shift which results in this rearrangements of spin parities for the ground state using the Thomas-Hermann effect that you mentioned at the very beginning of your talk?
Right. So I think, in this case, it really shouldn't be the case. If you look at how well bound, with respect to particle emission, strontium 73 and bromine 73 are, that really shouldn't play much of a role. Although given that it is potentially such a small shift, in my mind, I can't rule out weak binding. I should actually point one thing out, actually. So in some ways, our measurement is a little deficient, because when you're looking at these mirror energy differences, right, you want the actual difference between the two states, right? And so in our case, we only are able to say anything about the ground state of strontium 73. And so where the excited 1/2 minus state would be, we don't actually have any information on that. So we actually don't know how big the mirror energy difference between the states are between the mirror nuclei. So it could be much larger, and in that case, that might rule out some certain effects from dominating.
Yeah, I understand. I would just want to point out that we have to be really careful introducing isospin violating terms here, because really it may be very simple effect of being nucleon in the potential, and it's just Thomas Herman effect. And in bound nuclei like oxygen 17 and fluorine 17, this is 400 kilo-electron volts effect, even though a 1/2 plus is bound everywhere in both nuclei, right? So even for bound nuclei, Thomas Herman effect is plays a very important role.
Of course, yeah. I mean, I think that's actually the one thing that excites me about this is I don't know that we have enough data to really make a firm determination of what's causing this effect. So yeah, I think there's plenty of room to do more experiments, which is exciting.
Thank you.
So, I mean, you mentioned some future experimental program is trying to determine the excited state in the strontium, something that we will be able to do at F-RIB, for example.
Yeah, actually, that's a good thing to point out. So it may be possible, right? So if you look at the beam intensities that are put out there, that they say they might be able to achieve with F-RIB, this kind of experiment that took about a week to get a few hundred strontium-73 ions, you might be able to get that same amount in a couple hours with F-RIB. And so if that's the case, then yeah, I think there would be possibilities for looking at the excited states, or even say doing like the beta NMR measurement on strontium-73. That could be a possibility then too.
Very good. Let's see, any more questions or comments for Dan? I don't see at the moment.
I guess everything was just too clear.
It was crystal clear. You cracked the talk. Very good, very good. So I guess if I don't see any more questions, let's thank Dan again, and good luck. And hopefully we'll see you all again in 2 weeks. So have a good and safe weekend coming ahead. Thank you all. So Dan, I was trying to